But for transportation, it's one-time deal. So, okay, we spend maybe $100,000, $200,000 on this steel, and we throw it away after that. Okay, this is the transportation on the sea. You can. What I wanted to show here is the proportion of the barge. You see the barge and the module. So in this case, this module is about 100 feet. It's crossing the Panama Canal, I think. Here, yeah, here it says crossing the Panama Canal, which at the smallest size is 100 feet. But this is a 100 feet barge. Remember this picture, because I'm going to see this picture. Look at the proportions of the barge to the height of the module. And now, if somebody watches this movie, Deadly Catch, you can see what may happen if you have waves or a storm here. You know, I don't know, anybody watches Deadly Catch? It's on National Geographic. It shows, you know, how really a boat is really very small compared to the ocean, and when there are waves, then all this can move tremendously. And as I said, the barge dimension 400 by 100 by 20. Now again, what is the effect on the structure? That's what's important for us, is that the sea wave action produces 3 acceleration components. You can see, you know, the barge is rocking like this because of the waves, and they're rocking longitudinally and going up and down. And all this is similar to an earthquake for the module. It translates into 3 acceleration components. And to give you an idea, for instance, this is almost 2 times what it experienced, 2 times more than an earthquake in California. If you had an earthquake in California, a strong earthquake in California, you would have half the effect of what these modules will feel when there is a rocking phenomena due to waves.
You design more than 1 G for
Not more than 1 G. We design almost 0.8 G. But 1 G at the top, yes, of course. It can reach 1.2 G, 1.3 G. Now there are new studies that want to push this even to 2G, but I don't know. We are negotiating with this because it depends on the naval architect, and depends how to approach also. Some say that the waves will create that much. You know, it's all simulation. Now, of course, people are wise. If there is a storm, you are not going, to face the storm and challenge the storm. So normally, Mike McKenna will explain this, but normally we have harbors. Yeah, the button doesn't work in this case. So you pray that there, logistics will ahead of time identify harbors. So if the wave, and also they follow the weather and all this, and if there is a storm coming, then they try to go into a harbor and stay a couple of hours or 2 days. It's better than risking the multi-million expense of a module. We do not want to challenge the storm. We want to just arrive safely at port. Okay. There is another phenomena also that's called the sagging and hogging and sagging of the barge itself. So all this is combined together. And now, how is the module tied to the barge? That's also a structural item. You see these stub columns? They are sitting on the barge, and they are tied to the barge. They are not welded. They are tied by some kind of clamps. And to give it a little bit of a freedom, to be able to not move, hopefully not move, but breathe, So instead of welding it. The ties are welded to the barge, but they are bolted, or they are clamping the bottom of the stub columns. Okay, and finally, we arrived safely, and the RTV is taking it here and placing it next to its big brother here, which is there already. So, how do we set it? And the stub columns, they set on piles, you know, because Lou was explaining that most of the time the foundations are concrete, but on the North Slope, for instance, we have large piles, maybe 24-inch or 30-inch piles, and they have a plate, and they receive the stub columns, and they are put safely here, and then they are tied. Again, we use tie-down clips, plates, so that later on, if there is wind or seismic on this, also this is designed to take all the wind or seismic. Sometimes for the temperature, we put them on the sliding plate also, but different designs, you know, details. And then the happy ending. Any questions first?
Yes, I do have a question.
Yes.
How long does it take to unload one of these modules when it gets up to the site? Is it like a one-day thing? Or?
Mike?
Just unload it. It probably goes 8 hours when we return depending on that product. So a day, 2 days.
Now there is something that Mike will explain later, or how the RTV goes on the barge to raise the module. There is all balancing the barge. What do you call this? Equalizing the loads, fill water, one compartment, the other compartment, or etc. Ballasting. Yeah, ballasting, deballasting, all this is. Yeah, quite some more details. Mike will give a very, you know, interesting presentation. You have a question?
How do the extra beams you put in there overcome the deflection? What do they push against the top?
The beams, always, as Lou explained, all the loads have to reach the foundation. That's the path. So the beams, any force in the beam, and because they are moment connected, so any force, vertical force definitely will go. It's very simple. A beam has vertical force. It goes to reactions on the column, and they go down to the foundation, no problem. But lateral forces are taken by the deflection of the frame and the moment that is created by the joints. Now,
She's asking about the extra steel for the movement, right? Yeah, the one that is
okay.
She's asking about that.
Oh, okay. Oh, this one.
No.
So what you are asking is, how these forces help?
What do they push against?
Okay. You see, these are attached to the module steel. See, this is the module steel. There are beams here inside the module. Here. There is here also beams, longitudinal beam inside the module. So, for instance, here this is faint. Here maybe is better. You can see this is a member that goes and is attached to a horizontal beam from this side to this side, and then it goes back to here. See, it makes a frame. Now we have another frame at the lower level here. See. So they are all balanced. A force going up here is balanced by a force going up here, because normally you will have equal force everywhere. So we do not expect one force from one side, not the other. It will be equal. So the two forces come like this, and then they balance, they go up, and then they are balancing each other in the beam. So the beam will be under compression, for instance. That's not a regular beam. That will be under compression. And we have to design for this, of course. It will show in our analysis. Yes.
You're piping, right?
You are piping?
No,
Rotating, okay. Any other question?
What about Tundra and Foundation?
Foundation Tundra. What about it?
How you support the modules?
No.
Oh, the piles, you mean?
Yeah.
How these heavy
Yes.
modules are supported with regard to foundation.
Right. Yeah, we have those piles, you know, they go deep enough. But I did not prepare this. Time is kind of limited. Yeah, for the break. But if you need, you need to know about it, I'll explain to you in the office. Anybody else is interested in piles?
I think you keep on mentioning North Slope. North Slope is above the Arctic Circle, so above that the ground is always frozen. So the piles are supported by the ice.
Yes.
And the purpose also of the module being elevated, one of that is so you have a continuous air circulation around the module. You will not melt the permafrost.
Okay, yeah.
Great.
Okay, thank you very much.